natural disasters are constantly occurring all around the Earth. Yet, Japan is one of the world's most disaster-prone countries, as it experiences a variety of calamities every year. However, that environment has given rise to a great deal of knowledge and experience with disasters. J Innovators Takumi is a popular segment on Science View. We'll introduce several revolutionary inventions by Japan's Takumi that have enabled significant advancements in disaster prevention technology.
Science View is a regular program broadcast on NHK World that features Japanese science and technology. Today we're bringing you a special edition featuring Japan's Takumi, which I report on the J Innovators section of the show. The subject of our program today is disaster prevention through preparedness. We invited Assistant Professor Megumi Sugimoto of the Institute of Decision Science for Sustainable Society at Kyushu University to join us as a commentator. Thank you for coming.
It's my pleasure.
Dr. Sugimoto, I know that you specialize in risk management for disasters and are working hard at disaster prevention and recovery work overseas. First, could you tell us about the characteristics of Japan's natural disasters?
Certainly, Japan has some of the most disasters involving water and stand out for earthquake damage. This is a list of natural disasters that have occurred recently in Japan, where there was significant damage. In each of these disasters, more than 10 people were killed or went missing.
I remember reporting on these large disasters for other news programs, yet looking at this list again, it really seems that large disasters are happening every year. Floods, earthquakes, volcanic eruptions, there are all types of disasters. That's why, as we reflect on these natural disasters, I'd like to introduce technologies from various Takumi that can prevent disasters or help protect our safety and well-being after one has occurred. First, we'll look at the flooding caused by the torrential rains in the Kanto and Tohoku areas in 2015.
September 2015, eastern Japan was attacked by record torrential rain. Several places in the northern part of the Kanto regions had a total of more than 600 millimeters of rain over 4 days. A sudden increase of water in the Kinu River that runs through the city of Joso in Ibaraki Prefecture caused the river's levee to burst. Due to flooding from this breach, 40 square kilometers, about 1/3 of the total land of Joso City, was submerged. Approximately 4,300 people who were unable to escape had to be rescued by helicopter or boat.
I'm at an area which was heavily affected by a river embankment that burst in 2015 due to heavy torrential rain. Torrents of muddy water enveloped the area, destroying over 50 houses. What you see over there is a river embankment that collapsed. It is now 2.5 years since the collapse, and the reconstruction work has finished. Let's go and have a look. Over there is the Kinu River. This is the ordinary water level. The embankment was repaired and enlarged to be 2 meters wider and taller than the previous one. We spoke to the person in charge of river management for the Kinu River.
As you can see, there are a few new homes over there. These homes are new because the previous structures were washed away by the torrent of river water. They were rebuilt in the same location.
Why did the embankment fail here?
This area's embankment was built a little low. The water level of the Kinu River rose up and over the embankment. The water overflowed into the residential area on this side of the embankment, and the water rapidly started to erode the embankment until it completely failed.
I see. So the water level was greater than the embankment could handle.
That's correct.
The unexpected collapse of the embankment caused a complex disaster with houses washed away and destroyed and lifelines that broke down. We could say that this happened especially because the infrastructure was well developed, and on the other hand, Japan's aging infrastructure could cause a major problem in the future. The embankment in this area was built in the 1940s. The old infrastructure may not be able to withstand natural future disasters such as earthquakes and floods. Therefore, it is important to quickly find sections that have deteriorated with age and deal with them promptly. There's a Takumi who is trying to solve such problems with this innovative device. Highways and bridges are an essential part of our daily lives. But these infrastructures are rapidly showing signs of aging and are posing a threat to public safety. Mino City is located at the north of Osaka Prefecture. Hello, I'm Michelle Yamamoto.
I'm Nakaniwa.
This is today's Takumi or innovator, Kazuhide Nakaniwa. He runs a construction site surveying company that takes measurements during construction projects. The device next to the Takumi was created to tackle the problem of an aging and deteriorating infrastructure.
Right now, we are using the device to measure the cracks in that bridge.
Viewed normally, there aren't any visible cracks. But when you look through the device, wow, you can really see it up close. It's almost like using a telescope. The cracks are clearly visible from 20 meters away. But detecting cracks isn't the only thing this device can do. It can load the data into a computer as a 3D image. A detailed study of the cracks is needed to assess the state of an infrastructure. But until now, cracks were measured with a special ruler that was placed directly on the crack. To do this, it was necessary to bring in a crane car or build a scaffold. And most crack records were drawn by hand. A comment from one of his on-site workers motivated the Takumi to create this crack measurement system.
He said, "Why do engineers have to draw sketches?" That question got me thinking.
This was the resulting device. You can observe cracks from a distance and keep a precise record of its shape. The Takumi's knowledge and experience in the field helped him develop the device. Laser measurement technology was used to measure accurately from a distance. With the press of a button, the Takumi's crack measurement system emits a laser beam which hits the wall and bounces back to the device.
The distance is 3 meters, 46 centimeters, and 2.2 millimeters.
It can accurately measure up to 1/10 of a millimeter. The viewfinder is equipped with a scale that's used to measure the width of a crack. By finding the scale line that matches the crack, they can calculate the crack's width based on the distance. But there was still one problem. The width is different depending on where you look at it from. This vertical line looks much thinner from the side. Let's use these lines as an example. The greater the angle, the thinner they appear. The angle affected the accuracy of the reading. To remedy this, the Takumi's device has a function that makes adjustments as necessary.
It seeks out the incidence angle and uses it to calculate the width.
It needs the incidence angle of the crack. The key is to measure the distance between 3 points near the crack. By calculating the numbers, the device is able to find the incidence angle. Then, based on the incidence angle, it can calculate the actual width of the crack. This was how the concrete crack measurement system, which can detect signs of deterioration from a distance, was developed. The deterioration of infrastructures. The Takumi believes that this problem extends well beyond Japan.
Infrastructures are directly connected to human lives. I want to prevent developing countries from making the same mistakes as developed countries. I hope that they will take an interest in maintenance and work to detect cracks at an early stage.
The Takumi's device is sure to play an important role in Japan, where measures for aging infrastructure are in high demand. And I'm by the riverside about 800 meters from the area that had collapsed. And here is a floodgate. Normally it is open to allow the water from outside of the embankment to flow into the river. But when there is heavy rain and the water level rises, the gate is shut closed to prevent flooding. During the heavy rainfall in 2015, the local official in charge closed it by hand, but it is a very dangerous task to do when the water level is rising. And that is why one Takumi developed a floodgate which opens and closes automatically depending on the water level. Hello, I'm Michelle. Nice to meet you.
Oh, thank you for coming. I'm Hoshino.
Today's Takumi is the president of a floodgate manufacturer, Kyosuke Hoshino. We went straight in to see the floodgate his company invented.
This is one of our floodgates, although it's not finished yet.
Oh, so this is it. This is one of the Takumi's floodgates that has been installed on a riverbank close by. In hearing that the gate required neither an operator nor any power, I had imagined a sophisticated high-tech device, but it turns out to be a very simple mechanism. The most important elements are the weight at the top of the gate called a balance weight, and a float on the inner side of the gate. The gate's mechanism for opening and closing works like this. When there's heavy rainfall and the rainwater accumulates on the right side, the gate will be pushed to the left side. Then, with just that slight force, the balance weight falls to the right side, opening the gate to the left. By the principle of leverage, a gate that weighs more than 500 kilograms can open automatically with changes in the water level. On the other hand, when the level of the river rises due to backflow from high tides or tsunamis, the gate will be pushed to the right and the balance weight will return to the left. The float will gain buoyancy, and that force then causes the gate to shut tight. This automatic floodgate is designed to open and close using the power of leverage and buoyancy, but no electric or other power source. Many conventional floodgates require winding or other manual operation to be opened. A person must be available to check the water level and manually open and close the gate. In fact, when the huge tsunamis hit northeast Japan in March 2011, many volunteer firemen lost their lives in trying to operate floodgates.
By using our floodgate, what once required a human hand can be achieved without any operator. That can save lives.
But he encountered more than his share of difficulties in reaching this point.
Well, we went through endless trials and many errors. We got a lot of negative remarks. It wasn't easy. Also, achieving balance with the actual device using the calculations we had made was very difficult. It was hard to make it work as we had figured it.
It is 15 years since the Takumi's company first started development of this mechanical automatic floodgate. Added to the difficulties they had in the design phase, without a proven track record, it was difficult to get the device accepted.
People are always afraid to take a risk on something new. They go on using what they know without questioning it and feel safe that way. So, to change that and convince people with that mindset, we had to keep on telling them how good, how effective it is. It was an uphill battle, I can tell you.
Even after the floodgate had been installed, to obtain government recognition, they needed to carry out testing and demonstrations over and over. All their hard work paid off in 2012. The floodgate was selected by a government ministry as a recommended technology. This triggered widespread recognition of the device.
I want to take this all over the world. If this could be of use to others, I would love to take on that challenge. I really hope to be able to do that.
The Takumi's auto gates had been adopted in 3 locations among the Great East Japan earthquake disaster areas, and all of them operated normally. And thanks to those results, the gates were installed in many more places later on. And now in 2018, nearly 1,700 gates have been installed around Japan, and I heard that they're fully demonstrating that functionality.
Considering that it can be quickly used even where the electric power situation is poor, this really is incredible technology. I hope this can be used more and more for flood control, not just in Japan, but overseas as well.
And what did you think of the crack measurement system?
Much of Japan's infrastructure was built in the 1960s and 1970s, during what is known as the high economic growth period. Now Japan is facing a significant problem as that infrastructure ages. So I think this equipment is really necessary. This technology seems really useful for disaster prevention, just like with the floodgates, as it is a means of acting preemptively before disaster strikes.
In our next segment, we will continue to look at disasters involving water. Water disasters are foreseeable to a certain extent, and countermeasures can be taken beforehand. However, since things can suddenly occur that exceed those predictions, there can be occasions when there's no time to evacuate.
From the night of August 19th, 2014, to the morning of the 20th, torrential rain concentrated on a narrow range of the city of Hiroshima. More than 300 millimeters of rain fell in 3 hours, and a large-scale landslide simultaneously occurred, causing the deaths of more than 70 people. The damage spread because the area which experienced the severe rainfall was a residential area close to the mountain with homes that were very close together, and it happened during a time when it was difficult to respond. This is also called an urban-type sediment disaster.
Sediment disasters happened in more than 100 areas within the city, and as reconstruction continues, the evidence of the disaster remains. One couple who had escaped danger by just a few meters shared about what it was like then.
The amount of rainfall seemed a little different. I was surprised to find that the windows were completely black. Muddy water had covered the entire window.
When we woke up, we saw that the homes around us were destroyed.
The home next door was half destroyed by the landslide, and the homes one level above were completely destroyed with 2 people killed. The husband showed us photos he took directly after the disaster. Is this really the top of the roof?
Yes.
The sediment flowed up to the top of the roof, nearly 3 meters from ground level. There weren't any signs that this was going to happen?
No, none at all. We were talking about how the rain would stop before long. Yet, that's not what happened. Instead, we gradually became trapped. That's why this unanticipated situation gave us such a scare.
The affected area had not experienced a major disaster in recent years, so many who lived in the area did not expect a large landslide to occur. Furthermore, it is said that what added to the disaster was that the evacuation call from the local government was too late. It is truly difficult to predict a large-scale landslide. That is why our next Takumi is tackling the difficulty in an innovative way to foresee and alert inhabitants of the possibility of a landslide. We visited Okayama City, Okayama Prefecture in Western Japan. Hello, I'm Michelle.
Hello, my name is Kengo Okada. Welcome to Okayama.
Thank you for having me today.
Thank you.
Today's Takumi is Kengo Okada. His company manufactures stakes that are used to mark things like boundaries. The company also runs a stake museum displaying around 50 types of stakes from 10 countries around the world. This is from the US. And this is from Germany. And this one is from France. It's interesting that each country has its own style. This is one of the company's own stakes. It looks roughly the same as the others. So what makes it special?
This is one of ours. Hold this tablet over it.
Something came up on the screen. What's this?
That's information sent from the stake.
The screen showed information about a road. The marks shown are spots that have already been inspected. There are also photos and detailed reports from each inspection.
Inside the stake, there's a radio frequency ID tag, like this one.
The radio frequency ID tag, or RFID tag, is 2 centimeters wide and protected by a shockproof material. It is located in the top part of the stake. Each tag is capable of storing data. A smartphone application reads data from the stake and forwards it onto an internet server where it can be viewed. And it doesn't even need a battery, because the passive RFID tag draws its power from radio waves from the smartphone. These stakes are also used in disaster areas. These images are from Japan's massive earthquake and tsunami in 2011. They document the disaster and also show planned reconstruction in that area. They're also developing stakes to help prevent disasters. They rattle the stake to simulate an earthquake or a landslide.
I just got an email.
Oh, what does it say?
It tells me how the stake is tilted, what angle, and in which direction.
How does this work? The secret is inside the stake. There's an accelerometer that detects ground vibrations. It's battery operated. When the stakes shift or move due to avalanches, landslides, or nearby construction work, that information is immediately sent to a nearby receiver. From there, it's relayed over the internet to companies and individuals by email. The stakes can also be built with sensors that detect rising water levels, such as from heavy rainfalls. These stakes are already in place in higher risk areas, helping to reduce damage from natural disasters. And there's something else very special about these stakes.
This is what we use to make the stakes.
These? But they're used plastic.
That's right. Recycled plastic films. We use these to make our stakes.
The stakes made of plastic are light and easily portable. The challenge was making them strong enough. To address this, they adjusted the balance of constituent polymers. with just the right balance, the stakes are both strong and durable. The recycled plastic is fed into a machine, melted, reshaped, and the stake is done. They are eager to find even more uses for their stakes.
Our recycling, sensors, and RFID tags all add value to our products. We want to offer this Japanese technology to the global community. For that, I want to come up with even more ways for the stakes to help prevent disasters.
What do you think of the stake?
It's very light. Landslide disasters are hard to anticipate clearly ahead of time, and they seem to occur instantaneously. In the case of Hiroshima, sediment disasters happen one after another in more than 100 places. If we could detect abnormalities in the ground as soon as possible and share that information with the community, we might be able to reduce the scope of the disaster. I really hope this technology is used for disaster prevention in the future.
Next, this is the third type of disaster. The Great East Japan earthquake that struck Japan in 2011 was followed by the 2016 Kumamoto earthquake, which was a 7 on the Japanese earthquake intensity scale.
The epicenter was about 102 kilometers away from the university where my lab is, and I felt the tremors at around 5 on the Japanese earthquake intensity scale. Right after it happened, I went out there to investigate. I will share about what it looked like there.
April 2016. An inland earthquake with a maximum of 7 on the Japanese earthquake intensity scale struck Kumamoto Prefecture. What was notable about this earthquake were the many aftershocks that followed. The earthquake even managed to collapse stone walls of Kumamoto Castle, built more than 400 years ago. In the village of Minami Aso, there was a large-scale landslide and the road was cut off. A large bridge more than 200 meters in length collapsed, and about 1,000 people were left stranded. More than 200 people perished in this disaster, including related deaths.
I've come to the village of Minami Aso, which experienced significant damage. Close to 2 years have passed since the earthquake, but even now the barren mountain surface indicates just how powerful the energy of the earthquake was. Lying ahead of us was supposed to be a large bridge, as you can see from the blue road sign. However, gaps in ground caused by the earthquake led to its collapse and destruction. Now all that is left is the road that led up to the bridge. Restoration work on the bridge is underway with the goal of reopening the road in fiscal year 2020. Mr. Fujimoto, who runs a farm in Minami Aso, evacuated to a gymnasium near his house right after the earthquake. We spoke with him about the hardship he faced.
We couldn't use our mobile phones at all, as there was no way to charge them. There wasn't any power. After a whole day passed, the town finally set up its emergency response headquarters. And so then we were able to take turns charging our phones there with an extension cord. I believe we were able to do this around the 3rd day.
So until then, you didn't have any TV or radio?
Not at all.
So you were completely cut off from any sort of information like that?
Yes.
Once the aftershock subsided, Fujimoto returned to his home, only to find another problem waiting. That was the water problem.
As I recall, tap water was not running for about a month. And even when the water finally did start running again, It smelled like sulfur and really wasn't potable at all. None of the people who returned to their homes and lifestyles drank that water. They had to make do with bottled water.
The damage from this earthquake forced up to around 180,000 people from Kumamoto Prefecture to evacuate. Many people worry about difficulty obtaining water or daily supplies. We will introduce two inventions that were used to aid those disaster victims.
The first invention we'll introduce that has greatly benefited disaster areas was developed by a company in Osaka Prefecture.
Hello.
This is Yoshiaki Maeda, today's Takumi or innovator. He first took us to see this device.
First of all, take a look at this.
This looks like a small power generator. What is it?
It's a water purifier that can convert seawater into drinking water.
In fact, this device is used to purify water in disaster situations. Not only seawater, but also water from rivers and lakes can be purified to drinking water standard. 16 of these machines were sent to areas hit by the earthquake in Tohoku in 2011, offering safe drinking water to a large number of people. The Takumi's device only uses 660 watts of electricity. That's half the amount required by a microwave oven. But he has also invented an even more efficient purifier, especially for disaster situations.
This is it.
This is an ordinary suitcase, isn't it?
That's what it looks like, yes.
So the device is inside?
Yes, the water purifier is inside it.
When it is opened up,
The nozzle comes out like this, and you can start purifying your water.
to test its performance, let's see it in action.
We first add this to the water source.
The mixture that Takumi prepared contains Chinese tea, coffee, and vinegar. He will now run it through the purifier. After the device is switched on, it starts purifying in just 15 seconds.
It's okay to drink now.
It's okay? Then I'll try some. It's so clear. Whoa, it's crystal clear. And you can't smell a thing now. Okay, let's give it a try. じゃあ、いただきます。There's not a hint of the other flavors you added. The result is plain to see. The coloring in the Chinese tea and coffee and the vinegar elements are all completely filtered out. The particles removed measure between 1 to 100 nanometers, too small for the average conventional water purifier to remove. Filters used in many conventional water purifiers are made using activated carbon or hollow fiber membrane and have pores as large as 100 to 1000 nanometers. Iron rust and bacteria are large in size, so they can be trapped by these filters. But matter smaller than that will get through the filter's pores. That matter can include toxic materials such as dioxins and viruses. The Takumi's purifier can remove just about all of these toxic substances. The secret lies in these filters. And the one that plays the most important role is number 3. We took a look inside. It contained a scroll-like tube. This is called a reverse osmosis membrane filter. It has tiny pores of 0.1 nanometers over its surface. Water molecules are 0.098 nanometers across, so they can clear the pores, but dioxins and viruses which are larger cannot get through. But the Takumi did face a problem. The membrane's pore size is not entirely uniform when manufactured, so he could not remove all of the toxic material to achieve the target benchmark level. After countless attempts, the Takumi had another idea. Toxic materials passed through the pores because they were so small. The Takumi's idea was to bunch them together to make a bigger mass so the filter would then catch them. It is the first filter which carries out that function, although the details are a trade secret. The material that is treated in the first filter passes through the second filter, and then it is caught by the reverse osmosis membranes in the third filter. Once it has passed through this stage, it has produced water with almost no impurities. But it is now known that high purity water not only actually tastes bad, but it is also not good for your health if consumed over an extended period of time. So the Takumi adds minerals derived from coral at the fourth filter stage. In this way, the Takumi's water purifier is able to produce high purity drinking water that also tastes good.
At the moment, we only offer premium water purifying devices. So now I would like to produce more reasonably priced models. I'm also working on a new water purifier that will reproduce the taste of different water minerals from around the world.
Meanwhile, one Takumi developed a helpful tool from his own experience. Hello, I'm Michelle.
Hello, I'm Kubota. Thank you for coming.
Today's Takumi is Masaaki Kubota, an engineer working at this factory. This is Hayabusa, the asteroid explorer, right?
That's right. Our company developed the batteries installed on Hayabusa.
The Takumi's company develops and manufactures batteries for space probes, storage batteries for cars, and many power supplies for other uses. And this is the innovative battery that the Takumi developed. It's very light. I was handed a cardboard box. It doesn't look anything like a battery. This is how it's used. First, push open the holes in the side of the box to let in oxygen. Next, pour 2 liters of water in the box using the containers provided. After waiting for a few minutes, the connecting part lights up. Now it's ready to supply energy to other devices. Once water is poured in, this power-generating device can charge a smartphone up to 30 times. But why did the Takumi decide to develop this kind of battery? Actually, its development was closely related to the Great East Japan earthquake and tsunami that occurred in March 2011. The factory that was in Iwaki City, Fukushima Prefecture, was heavily damaged.
Power was out in many areas during the disaster, and it was difficult to charge cell phones. As a battery manufacturer, I felt we needed to create an easy-to-use power source for emergencies.
Many emergency charging devices typically use dry cell batteries, but their shortcoming is that the power capacity will decrease while being stored. Some cannot be used in times of need. So the Takumi thought of developing a long-lasting battery for emergency use. And this is his creation, a magnesium air battery. Because the chemical reaction only starts when water is added, it barely deteriorates during storage. This is how it works. When water is poured into the box, it mixes with salt and creates an electrolytic solution. Then the magnesium, which is the negative electrode, emits positive ions and electrons. On the other hand, the structure of the positive electrode is called an air electrode. The metal is covered with a carbon material. The air electrode does not allow water to pass through, but does let oxygen enter from the air vents. The oxygen that enters from the outside reacts with water and the electrons on the surface of the carbon and creates hydroxide ions.
The battery uses this principle to create a chemical reaction that can generate power. This air electrode is key. In the battery system, the carbon sheet that covers the metal needs to let only air pass through, but not water. The Takumi repeatedly mixed different substances with carbon. After 1 year of development, he finally created a carbon sheet that performed as required. The Takumi also paid special attention to the kind of water that could be used in emergencies.
In a state of emergency, there is no need to use clean drinking water. Seawater, river water, or rainwater could also be used.
It's perfect for emergency situations. The development of this battery started immediately, just 2 months after the Great East Japan earthquake and tsunami in 2011. The battery was commercialized 3 years later. The battery performance was rated highly, and a smaller compact version was also commercialized the following year.
In the future, I would like to develop batteries that can run household electronic appliances, such as refrigerators or microwave ovens. That's what I'm hoping for.
Those two inventions are items I'd want to recommend for a disaster area. Both of them were actually used in evacuation shelters after the Kumamoto earthquake, and I heard they really came in handy. Mr. Fujimoto said he did not have a chance to use them, but if he could have, I'm sure the situation would have been considerably better.
Mr. Fujimoto said that there was a smell of sulfur in the water pipes after recovery, but the Takumi's water purifier would have been able to turn that water into fresh water.
That's right. Also, what really helps in disaster areas is accurate information. You are virtually guaranteed to have false rumors flying around in the disaster area. It is up to the individual to accept or reject such information, but unnecessary false rumors cause even more alarm to disaster victims. During a time like that, a device that will help one obtain information is a very encouraging item. However, most devices will not work if there is no power. A battery that works simply with water, even if it is impure, is a really amazing technology.
Very true. So, Dr. Sugimoto, how would you wrap up today's program on Japan's disaster prevention technology?
The desire to protect life lies at the heart of the various technology developed by the different Takumi. I was really touched by this. That being said, it is dangerous to put too much faith in science and technology. Science is always developing, and no machine is guaranteed to never break down. In an emergency, the only thing you can count on is yourself. That is why it is important to be prepared on a regular basis and develop the habit of evacuating to a safe place as quickly as possible in an emergency. Ultimately, your own decision will be what saves lives.
Thank you very much. And this concludes our program today, but going forward, we'll continue to share many different examples of Japanese technology on Science View. Please stay tuned.